So I'm saying here that we're going to assume that my of xy minus my of x star y star is less than epsilon 1. And we can prove that this would be the case if you let your delta x and delta y shrink down enough. Now, we haven't proven that, but this isn't too hard to prove. Okay, so let's just assume that we've proven that my only changes, my only differs at most by epsilon 1 from its value at our sample point. That's the point. Okay? And that this happens for all x in R, where R is the region. Okay? So I need to specify this. So there's a region R. Okay? Then, for all x and all x values within the region, we conclude that the magnitude of this minus this with respect to y is less than epsilon 1 delta y. Because, of course, the magnitude of this difference has to be less than epsilon 1. So if something has a magnitude less than epsilon 1 and you're evaluating it over an interval of length delta y, the result's got to be less than epsilon 1 delta y. Okay, the magnitude of the result has to be less than epsilon 1 delta y. It then follows that this integral of the difference, follows that the integral of my of xy dy, the integral of this part, and then, of course, the integral of this with respect to y, this being constant, because my at x star y star is just a single value, and that single value that we want to get, that we want to focus on, the single value that kind of everything pivots around, and there we have it. This my of x star y star delta y then represents the integral of this over this interval. Okay, the my of x star y star being constant, its integral over the interval of length delta y is just this. So that the integral of my of xy delta y has to be within plus or minus epsilon 1 delta y of the product my of x star y star delta y. And why is that important? Well, now we've restricted how much difference you can have between a value of m down here and the corresponding value of the same x up here. It can't be, I think I said that wrong. What we want to say is that the difference between the value down here and up here is about equal to my of x star y star delta y. Now notice I've gotten rid of that y naught and x naught that was bothering me before, okay? And why is that important? Well, again, this says that the actual difference between here and here, which is this integral, differs from this approximation based on the value of my at this one sample point by only a small quantity, okay? That's a small number multiple of your delta y. That's going to be important. Okay, well, then it follows, got a few dots there because I didn't have room to write it, that the integral from y to y plus delta y of m of xy dy, which is the integral we're interested in, again, tells us the difference between the value here and the value here, has to be less than my of x star y star delta y plus epsilon 1 delta y. And it has to be greater than the same thing minus epsilon 1 delta y. So I'll do this, minus epsilon 1 delta y. And I still don't have room to write this out coherently, so you need to fill that in. Okay? So, what I say now, the thing I've been getting at all along is m of xy plus delta y minus m of xy equals the integral from y to y plus delta y of this, so we can make a conclusion about the difference of these. And then we want to draw a conclusion about the integral from x to x plus delta x of m of xy dx minus the integral from x plus delta x to x of m of x y plus delta y dx. In other words, this is the integral over part 1 of the path, and this is the integral over part 2 of the path. And I could say integral of m dx over part 1 minus the integral of m dx over part 3. Okay? And then we want to pull that together and see what the relevance of that is to the conclusion we want to make, at least for this small rectangle. And then what we get if we add up a bunch of small rectangles, because any region that Green's theorem applies to can essentially be broken up into small rectangles. Now, we haven't talked about that part, but when we build up the global, we're going to use these small rectangles. We can partition the region essentially into small rectangles, except right at the boundary, and we can take care of that easily. Okay? So you see, hopefully, the relevance of this, and you can make the analogous argument for the n function. Now, I used epsilon 1 here. Then for the n function, if you make the argument, you're probably going to use epsilon 2. See how close you could get to at least proving the theorem, let's say, for any region that can be broken up into small rectangles. Okay? Now how we put those rectangles together and how we conclude for the boundary, we'll leave that a little bit vague right now. But that part is really pretty easy. Okay, so I suggest maybe you think about how this might be done and how you might gain really deep insight into the global, local to global process.